Hi, AP Statistics, and welcome to Chapter 3.2. We're going to talk about the least squares regression line. You guys probably learned a little bit about this during Algebra 1, but we're going to get in depth and describe the formulas that are used to form a least squares regression line equation, how to interpret it, and a lot of other stuff. As a matter of fact, here it is, right? So we're going to interpret the slope and the y-intercept of the least squares regression line. We're going to make predictions. We're going to talk about extrapolation. We're going to calculate and interpret our residuals. We're going to make a residual plot. And we'll definitely work on that a lot tomorrow. We'll make, as I said, the equation. And we'll talk about R-squared values that tell us how well our least squares regression line models the relationship between two variables. So here we go. Let's go. Let's do it. All right. So our regression line, right? Some people have seen a line of best fit possibly in Algebra 1. This one is much more robust. And so and the reason why we do this is to make a prediction for a given y value, when we are inputting an x value, right? So in real life, right, if we have miles driven as our explanatory variable and our price in dollars for our response variable, what we want to do, so we can predict, if we notice, there is no x value for 10,000 or 100,000, right? So we don't have an x value here. We would be able to use our least squares regression line to make a prediction for our price in dollars for 100,000 miles driven. So that's what we're getting at. That's why we use a least squares regression line. Okay, when we interpret this, there are two ways to look at it. Remember I told you that this y with the little hat on it, it's called y hat. B is our slope in this case, right? So remember, this resembles closely y equals b plus mx, right? Where, remember, or the way that you're used to seeing it, y equals mx plus b, where this is your slope and this is your y-intercept. Same thing, just in a different package. All right? So we'll be able to interpret this. Okay, so here we go. We have some context with our graph that we had before. You can't really see very well our equation. It looks like y hat equals, gosh, I'm going to have to make this 3825. There's another number out there, minus 0.1629 x. It probably looks something like that. Okay. And this is 257. There we go. We can see from down below here. All right. So what are we looking at? We're looking at the price of a car. In this particular case, a Ford F-150, based on how many miles it has been driven. So what we could do, again, is predict the price of a Ford F-150 that has been driven 100,000 miles. All right, our slope B tells us that we would predict for the price of an F-150 to go down by $0.1629 for each additional mile the truck has been driven. And we'll use that to interpret some real data that we're looking at as well. All right. If we are going to make a prediction, we can simply input an x value, right? And then calculate our corresponding y value. There it is, quite simple. Extrapolation is when we use a value far outside of our data range in order to make a prediction. So for instance, if we look back at this data, I would be extrapolating if I was to make a prediction about a Ford F-150 with 250,000 miles on it. It's probably going to be actually quite strange, and it's way outside of the data range that we're using to create our least squares regression line. So, residuals. So what a residual is, right? It's the difference between our observed y value and the y value that we would get from our prediction, or the y value on our least squares regression line. All right, so we could subtract our y value that we get for a given x value on our least squares regression line from the actual y value from the data, and that gives us our residual. We'll find some residuals of our math grade ACT data that we've come up with. Okay, our least squares regression line produces residuals. Right, and what this does is it actually reduces the sum of the squared residuals. So our least squares regression line essentially is the line that has the smallest amount of residuals on average. We can get our residual plots. Essentially what we do is we have the same x values if we were to create a residual plot. What we do is we use the same x values, but now instead of using the y values given from the data in our original scatter plot, our new y value, so for this one, our new y value is going to be our predicted, or rather, our actual y value, data point, minus our predicted y value that we would get from our least squares regression line. All right, great stuff and good pictures to look at. If we see a clear pattern in our residual plot, a linear model is not going to work out for this. And you can tell, if you imagine drawing a line through some exponential data, right? So imagine I had something that was roughly exponential, right? Something like that, right? Imagine if we come up with a least squares regression line, something weird is going to happen, right? We're going to have a bunch of residuals down here that are negative. and 0 that are positive, right? But then up here, we have a bunch of residuals that are positive when we subtract our predicted from our actual data points. And that is what leads to us having a pattern that looks like that, right? Okay, we're also going to talk about the standard deviation of our residuals, which we're really getting from y values, right? So, and what this gives us is the size of a typical or maybe average prediction error. All right, our coefficient of determination. Sometimes students have a difficult time interpreting the coefficient of determination. And what it is it tells us the proportion of variability or variation in y that can be accounted for by the least squares regression line. And it's going to be a percentage or a proportion all the time. All right, so say we had an R squared value of 66.4%. Okay, we could say the sum of squared residuals has been reduced by 66.4% when using a linear model, for instance. All right, so, or we could say that 66.4% of the variation in whatever your y variable is in context is accounted for by the linear model that relates our response variable to our explanatory variable, right? And our variation in y is going to be measured by the sum of our squared residuals. Now, we'll get a chance to get that in the context, so that makes a whole lot more sense when we apply this to our data that we generated in class. All right, so let's look at these things. These residual plots, this standard deviation, and our R squared value, or our coefficient of determination value. So, we've been given this situation, right, where we have the relationship between the average number of points scored per game and the number of wins for 12 college football teams. So here we go, right? So it looks like as our points per game increases, our wins tend to increase as well. That makes perfect sense. And if I wanted to interpret this slope, I would say that we would expect for our number of wins to increase by 0.43 wins for every point increase in points per game. All right, if we look at our residual, it looks like we have a nice variation there, right? I don't see a big pattern, which means that it would be appropriate for us to use a least squares regression in order to model this particular relationship. S is 1.24, so our standard deviation of our residuals is 1.24. So what that's saying is that 1.24 is the size of a typical residual, right? So typically, our actual number of wins should be different from our predicted number of wins by 1.24. If we were to interpret this r squared value, you would say that approximately, or that 88% of the variability in points per game can be explained by, pardon me, back up. So our r squared value, or our coefficient of determination, is telling us that 88% of the variation in wins can be described by our least squares regression line, where our explanatory variable is points per game and our response variable is wins. All right, so if we are going to calculate a residual for a particular data point, fairly simple, right? We're being asked for the residual at this point, so we're going to plug it into our least squares regression line. We will get a predicted y value, and we will subtract it from our actual y value from our data. No problem. All right, so it looks like we did all of these things correct. All right, our computer regression output for now. Okay, for now, these values that have been with a border around them, that have been expressed with a border around them, are the only values that we're going to be looking at right now. Okay, so it's very, very important that you can interpret this mini-tab output. Okay, a lot of times on your AP exam, you will be given your data in this form. It won't say, hey, the standard deviation of the residual is this, and your slope is this, and your y-intercept is this. It's going to give you a mini-tab output instead, 9 times out of 10. And so you're just going to have to be able to know what's what. And this is a great picture of it for you. So do understand how to use this and know how to interpret each one of these values, to interpret your y-intercept, your slope, your s value, and your r squared value in context. In context is so important. Okay. So regression to the mean. Yeah, using technology is often the most convenient way. It's mostly, unless you only had like maybe at most 8 data points, you're going to really want to use your computer. So when we're calculating least squares regression line, we're going to have to first find our standard deviation of our y values, our standard deviation of our x values, right? And then we're going to also need to calculate an R value, right, which I've shown you how to calculate. That could take a very long time. Clearly, a distinction between explanatory and response variables is very, very important. Okay? For instance, if you switch them up, things do definitely change quite a bit. You wind up with some different, you would wind up having some interesting different types of predictions. Your standard error can change a lot. Notice, though, the R squared value is resistant to switching your explanatory and response variables. Okay. This one looks great, right? We could definitely use least squares regression to describe that relationship. This one, definitely not, right? This one's not going to work very well either. You can tell that the residual plot for that is going to definitely have a strange pattern. This one will work though. So, what does that mean? Correlation of least squares regression lines are not resistant? They're saying not resistant to outliers. Outliers. So, if you take an outlier out, it changes, especially your R value, significantly. Significantly. So watch out for outliers, and it's going to be common for you to get a question that asks you how much an outlier affects one of these values that we talked about from our least squares regression line, right? R, S, and so on. Right? But especially our R values. R values are going to be changed quite a bit by outliers. So watch out for outliers. And we've talked about this. We talked about outliers in both the Y and the X direction, right? In the X direction, they may not have as large of residuals, but outliers in the Y direction will be quite large. And therefore, they're going to influence your least squares regression line and the data that you get from that significantly. Well, that's it. We did it. So tomorrow, let's go ahead and apply all of these things to our real data that we collected and make some interpretations using our least squares regression. Thanks for watching. Hope you have a wonderful evening. Take care.